Tonight, we are going to talk about death, not the death you are familiar with, not illness or accident or old age. We are going to talk about the most extreme, most violent, most physically astonishing way that the universe can end a human life. And we are going to do it step by step, with precision, because the physics of dying inside a black hole is not just terrifying, it is one of the strangest things that the laws of nature permit to happen to matter. By the end of tonight, you are going to understand exactly what a black hole would do to your body, in what order, and why each step is more bizarre than the last. And the final step, the one that happens at the very end, is something that physicists still argue about, because it may be the most disturbing thing that the laws of physics have ever produced. Let's start with what a black hole actually is, because almost everything people believe about black holes is either incomplete or wrong. A black hole is not a hole, it is not empty, it is not a void or an absence or a gap in space. A black hole is an object, it is matter, compressed to such an extreme density that its gravitational field becomes so strong that nothing, not matter, not energy, not light itself, can escape once it crosses a certain boundary. That boundary has a name, it is called the event horizon. And the event horizon is where our story begins. The event horizon is not a physical surface. There is no wall there, no membrane, no line you could see or touch. It is simply the mathematical boundary beyond which the escape velocity, the speed required to pull free of the gravitational field, exceeds the speed of light. Inside the event horizon, even light cannot move fast enough to escape. And since nothing in the universe can travel faster than light, nothing that crosses the event horizon can ever return. The event horizon is a one-way door written into the fabric of space-time itself. Most black holes that astronomers study fall into two categories: stellar mass black holes, which form when massive stars collapse at the end of their lives and range from about 3 to 100 times the mass of the Sun, and supermassive black holes, which sit at the centers of most large galaxies and range from millions to billions of solar masses. The black hole at the center of our own Milky Way, called Sagittarius A star, has a mass of about 4 million suns. The black hole at the center of the galaxy M87, the first black hole ever photographed, has a mass of 6.5 billion suns. The size of the event horizon, called the Schwarzschild radius, scales directly with mass. A stellar mass black hole might have an event horizon just a few kilometers across. Sagittarius A star has an event horizon roughly the size of the distance between the Sun and Mercury, and the largest known supermassive black holes have event horizons so vast that our entire solar system could fit inside them with room to spare. This distinction between small and large black holes matters enormously for what happens to you, and it is the first thing that surprises almost everyone who thinks carefully about this. If you fell into a stellar mass black hole, the kind formed by a collapsing star, you would be dead long before you reached the event horizon. The gravitational field of a small, dense black hole drops off so steeply with distance that the difference in gravitational pull between your head and your feet, even thousands of kilometers away, would be catastrophic. This difference is called tidal force, and it is the first thing a black hole does to you. Here is how tidal forces work. Gravity follows an inverse square law. The closer you are to a massive object, the stronger its gravitational pull, the farther away the weaker. If you are falling feet first toward a black hole, your feet are closer to the singularity than your head. That means your feet are being pulled harder than your head, and the difference in that pull, stretched across the length of your body, creates a force that attempts to elongate you along the direction of your fall. Simultaneously, the gravitational field also pulls your sides inward, compressing you laterally. The net effect is that your body is being stretched lengthwise and squeezed from the sides at the same time. Physicists have a name for this process. They call it spaghettification, and while the name sounds almost whimsical, the reality is not. For a stellar mass black hole, the tidal forces become lethal at a distance of thousands of kilometers from the event horizon. Your body would be pulled apart long before you got anywhere near the boundary. The forces acting on your feet versus your head would exceed what any biological tissue can withstand. You would first feel an extraordinary stretching sensation, then your circulatory system would fail as blood was pulled away from your brain toward your feet with overwhelming force. Then your body would begin to elongate, bones and muscles and organs stretching beyond their limits. Then you would simply come apart, not explosively, gradually, and then completely, stretched into a long, thin stream of particles falling toward the singularity. For a stellar mass black hole, spaghettification begins and ends well outside the event horizon. You never even make it through the door. But for a supermassive black hole, something completely different happens, and this is where the physics becomes genuinely strange. A supermassive black hole is so massive that its event horizon is so large that the tidal forces at the event horizon itself are actually very gentle. The difference in gravitational pull between your head and your feet at the event horizon of a black hole the size of Sagittarius A small is small enough that you would not feel it as dangerous. At the event horizon of a truly enormous supermassive black hole, billions of times the mass of the Sun, the tidal forces are so weak that you could cross the event horizon without feeling anything unusual at all. This is perhaps the most unsettling fact about black holes. You could fall through the event horizon of a large enough black hole and feel nothing, no wall, no signal, no alarm, no physical sensation that tells you something fundamental has changed. You would simply continue falling, but everything would have changed. You would have crossed the point of no return, and you would not know it until you looked back and realized that the universe outside was already unreachable. So let's follow you into a supermassive black hole. Let's say you are falling toward one of the largest known black holes, with an event horizon large enough that tidal forces at the boundary are negligible. Here is what happens, step by step. Step 1. The approach. As you fall toward the black hole from a great distance, you notice something happening to the light around you. The universe ahead of you, in the direction of your fall, begins to distort. The black hole's gravity bends light from stars and galaxies behind it, creating a ring of distorted, magnified light around the darkness at the center. This is gravitational lensing, and at sufficient proximity it produces a phenomenon called the photon ring, a bright circle of light where photons from across the universe have been bent into orbits around the black hole. The universe is beginning to look wrong in a way that has no parallel in everyday experience. As you approach, you also notice something strange about the darkness itself. The black hole does not look like a hole in space. It looks like a perfect sphere of absolute darkness, surrounded by an accretion disk, a swirling ring of superheated gas and dust that has been falling into the black hole over millions of years. This disk glows with extraordinary brightness, reaching temperatures of millions of degrees, radiating X-rays and visible light with a luminosity that can outshine entire galaxies. As you approach, this disk would be the brightest thing you have ever seen, brighter than the sun, brighter than any star, a ring of fire surrounding an abyss of perfect dark. But before we go further, let's talk about the firewall, because in 2012, a group of physicists led by Ahmed Almheri, Donald Maroff, Joseph Polchinski, and James Sully, collectively known by the acronym EMPS, proposed something that shook theoretical physics to its core. They argued that the gentle crossing of the event horizon, the whole idea that you would feel nothing unusual as you passed through, might be wrong, catastrophically wrong. Their argument goes like this. Quantum mechanics demands that the information falling into a black hole must eventually escape in the Hawking radiation. For this to happen, the particles of Hawking radiation escaping from just outside the event horizon must be quantum mechanically entangled with the particles that fell in before them. But quantum mechanics also has a rule called the monogamy of entanglement. A particle can only be maximally entangled with one other particle at a time. If the outgoing Hawking radiation particle is entangled with earlier radiation particles, it cannot simultaneously be entangled with the particle on the other side of the event horizon. And if that entanglement is broken, the mathematics shows that the event horizon would not be a gentle, empty boundary at all. It would be a wall of extremely high energy radiation, a firewall. Any infalling observer would not pass peacefully through the event horizon. They would be instantly and completely incinerated at the boundary. The firewall paradox placed physicists in an impossible position. Either the principle of unitarity is violated and information is destroyed, or the equivalence principle, the cornerstone of general relativity that says free-falling observers should feel nothing unusual at the event horizon, is violated and infalling observers are burned alive, or something else entirely is happening at the event horizon that no current theory can describe, no satisfying resolution has been found, the debate over the firewall is ongoing, and it means that even the step of crossing the event horizon, which we described as gentle and undetectable, is not something physics can guarantee with confidence. Step 2. Time dilation. Here is something that your friends watching from a safe distance would observe, and it is one of the most disorienting predictions of general relativity. As you fall toward the event horizon, your friends would see something strange. They would see you slow down, not because you are actually slowing down, but because the light reaching them from you is being increasingly redshifted and delayed by the black hole's gravity. From their perspective, your descent would appear to take longer and longer as you approached the event horizon. You would appear to freeze in place, your image growing dimmer and redder as the light from you struggled to escape the black hole's gravity. In theory, your friends would never see you cross the event horizon. Your image would fade and redden and slow to an eternal stillness, frozen at the boundary, a ghost of your final approach. From your perspective, none of this is happening. You feel no slowing. Time is passing normally for you. You cross the event horizon, and you feel nothing. But something profound has happened to time itself. Inside the event horizon, the mathematics of general relativity does something extraordinary. The dimension we normally call time and the dimension we call the radial direction toward the singularity effectively swap roles. Outside a black hole, you are free to move in any direction through space, but you are compelled to move forward through time. Inside the event horizon, you are free to move through what was previously time, but you are compelled to move in one direction through what was previously space, toward the singularity. The singularity is not in your future in the usual sense, it is in your spatial future. It is a place you are moving toward, not a moment you are moving toward. And there is nothing you can do to avoid reaching it, just as there is nothing you can do to avoid tomorrow. Step 3. Inside the event horizon, you are falling. The universe outside is still visible, but it looks wrong. The entire observable universe, all 2 trillion galaxies, all the light from all of cosmic history, is being compressed into a shrinking circle of light behind you. The black hole's gravity is focusing the light from the outside universe into a smaller and smaller region as you fall deeper. Around you and ahead of you is darkness, but behind you, in the direction you came from, the universe is contracting into a bright, distorted, increasingly alien-looking disk of light. There is something else happening that is worth pausing on. Because of the way gravity bends light inside the event horizon, if you looked in any direction other than directly toward the singularity, you would see light that originated from outside the black hole, bent around by the extreme curvature of space-time and delivered to your eyes from unexpected angles. The entire history of light that ever fell into this black hole, every photon, every signal, every flash of radiation from every star and galaxy that was ever consumed, is in some sense still present inside the event horizon, traveling inward. You would be surrounded by the accumulated light of billions of years of the black hole's existence, all of it converging, all of it falling with you toward the same inevitable destination. And there is something even stranger. Because of the way space-time behaves inside the event horizon, the concept of direction itself becomes distorted. Normally, you can point in any spatial direction and choose to move that way. Inside the event horizon, the direction toward the singularity is not just a direction you can choose to move toward. It is the direction of your future. Time, in a real mathematical sense, points toward the singularity. Choosing not to move toward the singularity inside a black hole is as impossible as choosing not to move forward in time. It is not a matter of insufficient thrust or inadequate technology. It is a fundamental restructuring of the geometry of space-time itself. You are still alive. Assuming the black hole is large enough, tidal forces have not yet become problematic. You could, in principle, survive for some time inside the event horizon. For a sufficiently massive black hole, the time between crossing the event horizon and reaching the singularity could be hours or even longer. You would have time to think, time to observe, time to understand what was happening even as you moved inexorably toward the end. But you cannot communicate any of this to the outside universe. Any signal you send, any light you emit, any radio wave or particle you try to broadcast is falling along with you toward the singularity. Nothing you do inside the event horizon can reach the outside. You are, in the most complete sense that physics allows, cut off from everything that came before. Step 4. Spaghettification begins. As you fall deeper, even for a supermassive black hole, the tidal forces begin to grow. The singularity is approaching, and as you get closer, the difference in gravitational pull across your body increases. First, you would notice a slight stretching sensation, a feeling of being pulled feet first with slightly more force than your head. Then that difference would increase. Your circulatory system would begin to struggle, blood being pulled toward your feet with increasing force. You would feel the stretching in your muscles, in your joints, in every cell of your body. It would not be fast. It would be gradual, and then it would not be gradual anymore. The process would accelerate. The forces would exceed what biology can withstand, and the spaghettification that for a stellar mass black hole happens outside the event horizon happens here, inside it, closer to the end. Your body would elongate, stretched by the differential gravity, compressed from the sides, pulled apart into a stream of particles and atoms and subatomic fragments, all still falling, all still accelerating toward the singularity. Step 5. The singularity. This is where physics breaks. The singularity is the point, or the region, at the center of a black hole where the mathematics of general relativity predicts infinite density and infinite space-time curvature. All the mass of the black hole is compressed into a point of zero volume and infinite density. Our equations produce infinities, and infinities in physics are almost always a sign that our equations are incomplete. They are telling us that something happens at the singularity that our current understanding of physics cannot describe. General relativity, the theory that predicted black holes and describes their structure with extraordinary accuracy, breaks down at the singularity. Quantum mechanics, the theory that governs the behavior of matter and energy at the smallest scales, is also inadequate by itself to describe what happens there. We need a theory of quantum gravity, a unified framework that combines both to describe the singularity, and we do not have one yet. The singularity is the place where the frontier of human understanding meets the limit of what our equations can tell us. What happens to the matter that reaches the singularity is genuinely unknown. Our best theories say it is compressed to infinite density, but infinite density is not a physical prediction. It is a mathematical signal that our theory has reached its limit. The truth of what happens at the singularity, what space and time become at that point, what happens to the information that was once you, is one of the deepest unsolved problems in all of physics. And this brings us to the final and most disturbing step, the one that happens after, the one that physicists argue about most fiercely. Step 6. The information paradox. Here is the problem. Quantum mechanics has a rule. One of its most fundamental and non-negotiable rules: information cannot be destroyed. Every quantum state, every configuration of particles, every piece of information encoded in the physical world must be preserved somewhere. It may be transformed, scrambled, redistributed, but it cannot simply cease to exist. This is called the principle of unitarity, and it is one of the pillars of quantum theory. But when you fall into a black hole, what happens to the information that was you? Your body is made of atoms. Each atom has a quantum state. Each particle has a quantum state. Every piece of information about what you are, what you have experienced, the precise configuration of every particle in your body, is encoded in quantum states. When you are spaghettified and reach the singularity, what happens to all of that information? Stephen Hawking showed in 1974 that black holes slowly evaporate. Through a quantum mechanical process now called Hawking radiation, black holes emit a faint thermal glow of particles created at the event horizon. Over an unimaginably long time, A black hole loses mass through this radiation until it eventually evaporates completely. And here is the problem. Hawking's original calculation showed that this radiation is perfectly thermal. It carries no information. It is the quantum equivalent of random noise, which means that when a black hole finally evaporates, all the information that ever fell into it, including the information that was you, is simply gone, destroyed, erased from the universe. This directly contradicts the principle of unitarity. If Hawking was right, black holes destroy information. If quantum mechanics is right, information cannot be destroyed. Both cannot be true simultaneously. This is the black hole information paradox, and it has been one of the central unsolved problems in theoretical physics for 50 years. Physicists have proposed many resolutions. Some argue that the information is somehow encoded in the Hawking radiation, scrambled beyond recognition but still present. This is the view favored by most string theorists and was argued forcefully by Leonard Susskind and Gerard Hoof. Some argue that information is stored on the event horizon in a two-dimensional encoding called a hologram. Some argue that small remnants of the black hole survive after evaporation, preserving the information within them. Some argue, following a recent and controversial calculation, that the information does escape in the Hawking radiation through a subtle quantum gravitational effect involving what are called quantum extremal surfaces. No resolution is universally accepted. The debate continues, and at the center of that debate is you, or rather what remains of you after the black hole has finished its work. Whether the information that was once your body, your mind, your memories, your precise quantum configuration survives the black hole's evaporation or is truly and permanently erased from the universe is a question that our best physics cannot yet answer. This is what makes black holes unlike anything else in the known universe. They are not just extreme environments. They are places where the laws of physics as we understand them become incomplete, where the deepest questions about the nature of information and reality and the structure of space-time are forced into the open. They are the universe's way of showing us the edges of our own understanding, and if you were to fall into one, you would be the only being in the history of the cosmos to experience that edge from the inside. You would cross the point of no return without feeling it. You would watch the universe compress behind you into a shrinking circle of ancient light. You would feel the pull of the singularity growing as you approached the place where our equations break. And then, at the very end, you would become part of the greatest unsolved mystery in physics. Not just dead, not just gone, but transformed into a question that the universe has not yet answered. A question about whether anything that ever existed can truly be erased. Whether the information of a life, every moment, every memory, every particle of every thought, can survive even the most extreme thing the universe can throw at it. The black hole does not simply kill you. It turns you into a problem that the smartest minds our species has ever produced cannot solve. And in a universe full of mysteries, that might be the most remarkable thing that can happen to anyone.